All right, so good evening, everyone. Let's just first say I had been a bit ill during this weekend, so if my voice would give in, I'm sorry in advance, but hopefully it's all fine and you'll be able to listen to me for all duration of this talk. So let us first start with the name of the presentation, because let's just say that I could have named it like how weed detection shapes the agriculture industry, but let's just say it wouldn't have the same ring as processing problematic plants with Python, right? So let us go over the agenda, what we'll be looking into tonight. Yeah, fair warning, I'm a person of academia, so if I would go too hard on you like the students, just show it and I'll try to change my presentation to more normal tone, but I'm too used to talk to students who are like not super interested, so I actually had prepared some interactive parts, but then the organizers told me to ditch it, so if you were hoping for some interaction, leave it for the questions at the end. Anyway, let us first look at why actually it matters and why it should interest you. So, the most cheeky question you can hear from agriculture is, have you eaten today? Then yes, it interests you. Let's just say that overall, the industry is the only one which is actually having the absence of the problem of having end to the demand, because if agriculture industry would run out of demand, like we're running out of people, so that would be bad. So hopefully it's going to grow on. Now, if we talk specifically about weeds, they're actually super important to the outputs of this industry. And those outputs are going to be more important in the future because, as you have probably read in the media, the population is still growing, and with it, its demand for food is growing as well. So therefore, some research was like 5 years ago predicting that we're actually going to need like 110% increase in our outputs, like of the yields of the crops we're producing, in order to be able to sustain our population in the next 50 years. The projections have changed a little bit because we are not on this track for 10 billion people, but mostly like 9.5 or something like that. So it's not that bad, but we're still above like 70% need increase. Now, weeds come to play in this because they are responsible for, let's just say, a third of production losses of agriculture worldwide. So imagine without those weeds, we would have 30% like this. Next to that, they are economically extremely important because according to most research, they actually make up to 65% of the work that the farmers are actually doing on field. So therefore, the importance is not only in terms of the production, but also in terms of the time that the farmers have to fight it. Now, how do we progress in this? Actually, the industry has been working on increasing its potential to get rid of weeds for quite some time. Actually, the biggest revolution was the use of chemical pesticides and herbicides during the 1950s and 60s. Back then, the increases were substantial. But the thing we're talking about today, being the automated weed detection, is relatively recent, with first research being done around the beginning of the new millennium. Now, the things that started back then were quite basic and were not able to really detect the weeds themselves, but were more working on the basis and presumption of with the spacing between the field. So basically, if you knew that the plant is somewhere and the weed should be somewhere else, you are just using probabilistic models to predict that it probably could be there, and by that use the sprayers more precisely. But the overall success rate of that was quite low, and the only real revolution we actually got was with the use of machine learning driven computer vision and its implementation on drone imagery being used for creation of maps for the spraying. Now, the business part of this thing is quite interesting because, like I described to you, the weeds are super important to the outputs. So if you imagine that like 80% of the inputs the farmer has to put in the field are being targeted at this 30% increase, you can imagine that if the farmers would be able to save up on this part of their inputs, it would be quite substantial. So imagine reducing those 80% by the potential 50% that some research was showcasing, and you get why it's actually quite appealing to the farmers to innovate and use some modern computer vision-based technologies to basically decrease the amount of herbicides you're using. Secondarily, there's the legislative support, because as you have probably heard from the media, we in the EU have pledged ourselves to reduce the use of pesticides by up to 50% by the year 2030. That's quite a substantial decrease, and once again, unless we give the farmers some sort of tools to actually achieve this level of reduction, we're going to see a brutal increase in the field losses conducted by the weeds I was talking about before. On the left side, you can also see a quite interesting map, because that's actually one of the biggest arguments the farmers are using against this reduction, because overall in Europe, the amount of use of pesticides varies quite a lot. So imagine that the Netherlands, having 10.9 kilograms of chemical substance per hectare, has an easier job reducing by 50% than, for example, Norway with 0.9 kilograms per hectare. Now, let us look at how we'll actually be able to do that. So the basic implementation, which is right now quite common. I mean, I'm describing it as something quite common, but overall there's like 6 academic teams in Europe which are actually working on this. So that's one of the issues that actually I'm going to be talking like quite generally, but this generalization isn't all the general. Like imagine 6 teams, so therefore, I mean, I have all those people who are working on this research in my contact book. So imagine if the future of your food supply relies on 6 teams. That's not really a good assumption. So anyway, it's basically based on neural networks of the YOLO family. I mean, if you would ask any of those researchers, they all basically realize that this real-time object detection is the best of the available tools, and they are implementing it quite widely. Now, the question they are also always being asked is whether to focus on real-time detections or on more substantial mapping of the areas which are being then processed and used afterwards. Basically deciding between the camera activating something on the spot, or between the camera basically creating a map for the sprayer to spray on the field and precisely target only those plants that are weeds and not the crops themselves. Now, one of the more interesting things for you is the spectrography of this point of view. Like basically, most of you are seeing work through this lens. This is the visible light. From majority of the research, we realized that it's quite useful in detection of the weeds, and it's actually a majority of the models which are running on the RGB videos. But because of its implementation and of its limitation, because let's just look at it, the picture, basically some of the weeds can be obscured, hidden, and covered by the dirt, which has different spectral elements in comparison to the plant itself. So therefore, we implemented near-infrared spectral band as well, and by combining those 3 bands, or 4 bands, my bad, sorry. Yeah, and you should come closer, because you're all,
When I was coming back, I noticed that you standing in the back might not really see what's on the slide, so feel free to make a couple of steps to the front or move your chairs a bit to the front so that you see a bit better, because these spectral images are pretty cool, but hey, they're also very detailed.
Yeah, right. I mean, you can see a lot of small plants, and that's the thing, because those plants are super small, and therefore if the model tries to detect them, it's much easier if it tries to detect them in the spectral band, which actually showcases the reflectance with a much higher contrast than just the RGB. And this simple combination of those 4 bands together to a single TIFF image is done, well, basically like everything in this point of research with Python. Now, the most important thing about the data itself is actually the fun stuff, because that's the biggest drawback of the weed research. Like, if you look at images, you can get thousands upon thousands of images of weeds and of crops. That's all nice, but how do you actually teach the neural network to differentiate between the crops and the weeds? Well, you annotate a lot. Like, basically, thanks to the diversity of those plants in the fields, it's actually super hard to find identical elements in those plants. So therefore, you need a data set to be as broad as possible. Therefore, majority of the research data sets starts with at least 2,000 objects per single class. And even then, it's super limited in its implications because, once again, the diversity is so high that basically you're going to see same species in two different growth stages, totally different. And therefore, this annotation problem is basically one of the biggest issues of the weed detection because, like I was describing to the organizers prior to this talk, there's a lot of people who know how to use computer vision. There's not that many people who can differentiate between the weed species. Those two groups don't combine. Like usually it's super hard to find a person who's doing both or who's at least cooperating with the person who's doing this stuff as well. And that's actually one of the biggest drawbacks of this research, where you basically try to look for people who help you implement computer vision on the great big data sets, which can be annotated only by people who actually understand the problem. And this will probably appear more in the future of the presentation, but there's this fun story about one unnamed German company, which is super interested in agri-industry. They basically try to go around this problem by outsourcing to India. Like, it's logical, a lot of companies are doing that, but can you imagine a person who lives his whole life in India differentiating between weeds which grow in Germany? Let's just say you all know how it ended up and how great the model was, that basically they ditched the whole project because it was such a sink for money, because they invested so much into that it made no sense, like to waste all the money on a model which wasn't able to differentiate between the species as, let's just say, if you look at this picture, those two are the same species, but if this one would have like 5 days more to grow, it would look totally different. And only person who's actually educated in weed research can truly differentiate between those species. And therefore, that's the biggest drawback of this research, as I was saying before. Then the next step would be the training of the neural network, which is something you all probably understand and know. And that's the simple stuff. That's basically just taking the data and making a model which actually learns on basis of the data. But the issue is, once again, that evaluation of these models needs to be done semi-manually, because the diversity of the things in fields is so high that even though you have this nice confusion matrix, you cannot really trust it too much, because when we are trying to use those models in the unbenign environment of outside, it actually flopped a lot, because all the plants are growing under different stresses, under different lighting conditions, and therefore the data once again changes from each day to the other one. One of the bigger questions which we should probably talk about as well is actually how much you want to innovate, because even though we would be able to fully automate the stuff, there's this dilemma whether it would be actually good to get rid of all the humans. That's the dilemma between having a human on the loop and in the loop. In terms of farming, is basically having a robot which just rows across the field and does its thing, which in Czechia it's actually illegal, because our beautiful law states it in a way that you can implement an autonomous robot on the field only when the field is fenced, but due to different regulation, you cannot actually build fences around fields. So therefore, you cannot really use those. And the other thing is that the effectiveness of this robot in comparison to those big tractors we're using in Czechia is, well, diminishes. Like most of the robots, I think I have a picture next slide, yeah. Most of those robots can take care of like 3 meters of the field at a time, and contrast that with a tractor which takes care of at least 12 meters with one go. Now, that's actually the other dilemma, whether we go for real-time detection, as I was describing before, or whether we go for the application maps, which might sound super interesting to you. Like it's super nice to use a drone, create an application map, and just give it to the farmer. Like, yeah, this is where the weeds are. This is where you should act. But the thing is that even though this is right now the mainstream approach, there's usually a delay. Imagine that you take the data on one day, you process it on the second day, and on the third day, you expect the farmer to act. Those 3 days can be enough for the plant to grow in a phase that the farmer is actually not able to get rid of it with the chemical and mechanical tools that are at his disposal. So even though this is like super interesting to the startup companies, which I mean, there's like 2 of them involve Europe, but it's super interesting to them because it sounds like a nice service. But if you consider it in the context of how agriculture actually works and how those systems are reliant on other subsystems of the field, it's actually not so nice to use this approach. Yeah, and this was my attempt at joking because this is actually one of the more interesting things about the wheat research. Like across all the teams that are working on it, everyone's using Python, like all of them. One thing is that it's relatively simple to learn, and most of those people are wheat scientists, so therefore they are not programmers, so therefore they need something that's simple for them to implement. Secondarily, there are so many libraries, like you were describing before, which are perfect for not only taking the data, changing it in a way that you combine the spectral planes, in the way that you can rotate it. Basically, all the adjustments you can make to data can be done simply by all those libraries that were presented before. And then also, majority of those neural networks are running on Python. So therefore, not only that the people are inclined to it because it's relatively easy to learn, but also because all the underlying technology is written on basis of Python. So therefore, majority of the people who are working in wheat research are actually using Python because it's just good for them. And that brings me to the darker side of that, because there's actually the issue of the absence of the nexus between the people who actually can use computer vision and between the people who know the weeds. So majority of the current research is actually done by teams in India and China, because for them it's super accessible, especially with large language models, which actually help you so much with writing the code. Like GPT can actually write a decent code, which brings you all the way from taking the pictures of the plants, all the way to implementing the neural network to train on them and to start up creating your own sprayer. But the thing is that if you look at the outputs, this is what you're competing with. Like, it's nice that the project happened. It's super nice that somebody's working on that. But do you think this is going to increase our yields by 110%? That's a lot of agreement, actually. Now, the thing is that this research is extremely underfunded, and even though it could have a strong economic potential, no one is really trying to invest and their time and money into that, because it's the agriculture, it's the dirty stuff for some. And even though there's small entry barrier into starting it, there's actually a lot of problems while implementing it on the larger scale. So, yeah, and that's the final slide I totally forgot about, because that's actually one thing that totally lacks there, and that's open source technology. Like all those models are running on open source stuff, like all the Python libraries, all the YOLO neural networks, but the final data sets and the final products are all non-open source. They are just focusing on creating something for their own profit. Like even the research teams are refusing to share their data. So that's actually going to be my call to action for you, even though you're not wheat scientists. But if you would actually have some connection to this research, try to share the data. It's going to help us all in creating more, pardon me. Like I said, this weekend was rough. Yeah, so share this data, because it's going to make us all more resilient and more capable in detecting these weeds and creating models that actually might as well create the outputs that are necessary by the population growth. Yeah, and now let us move to why you shouldn't be actually doing this, because there's a lot of issues with the research as well. Now, first thing first, it's actually super expensive to start doing that. Like basic model can be done on basis of the pictures from your mobile phone. That's all nice. But if you want actually real-time nice detections, you need much more than that. For example, this multispectral camera, which can be the basis of models we are using at academia, costs like 10,000 euros. And if you would want to use it on a sprayer, you need 40 of those. Now scale it up for each farm and each use, and you get why it's super expensive to actually think of implementing this technology on a larger scale. Then there's the absence of industry-centric models, because even this camera, like, it's nice, it does the job, but it's made for industry. Like, it's made for clean environments within factories. It's made for conveyor belts, which have the same lighting, which have stable temperatures and stuff like that. But then you throw it outside on a field. It's not resilient to dust. It's not resilient to major changes in lighting, and it's not resilient to all the industrial stuff shaking and moving on the field. So therefore, even though you would have some sort of sensor which actually would fulfill your criteria, you cannot actually use it on the field, because it's not, once again, created with agriculture in mind. Then there's computing integration being problematic, because all the large-scale stuff I was talking about, the sprayers, it costs a lot of money. So imagine trying to convince the big company like Bosch to actually try to change those things. Like one sprayer costs in millions of euros. And imagine trying to convince Bosch to actually change it. This is one of the hurdles that's actually slowing down the progress, because all those companies are focusing only on the large-scale industrial farming and don't want to actually scale down this technology for the now really communicated and proposed support for the small farmers. And finally, there's the production costs, which I actually talked about before, that being that you cannot outsource it, and therefore you need someone who actually understands the stuff and who can differentiate between the species. So therefore, if you can get actually a huge number of those people, you have to pay them well, because those people are usually from the academia and are not keen on annotating multiple hours for peanuts. So therefore, the production costs grow even with just this in mind, because that's the basis of the data, having someone to actually understand it. And finally, my favorite is that this environment is extremely unbenign. I was hoping to show you the video of this MIT turtle. You've probably all seen it. It's a rifle, but it's a turtle. And scale it up by like 20, and you get what the fields look like. Everything tries to work against you. Like the crops, we actually have a historical comparison we can compare it to, are quite used to having environment turn against them. So in terms of computer vision, you're one small mutation away from actually ditching the whole model. Because if you would selectively cull out all the weeds which are based in the model, which the model can describe and detect, then the only crops, or the weeds themselves, which would remain on the field are the ones which look differently. And therefore, the model cannot differentiate between them and the crops. Now, we've actually seen this historically with the resistance of weeds to herbicides. And it happened, so therefore we know that the environment is going to fight back. Now, how would we resolve that? With some sort of resilient, resistant computer vision? We actually don't know. But hopefully this is a problem for the future generation of the people who are working on this research, because let's just say that this repetitive negative selection of the mutations actually takes quite some time. Like with the resistance, it took, I think, 15-ish years. So therefore, it's not a problem for today, but it's a problem you should all keep in mind. Yeah, and the final hurdle for you should be the users themselves, because if you create something for the industry, yeah, the people will generally accept that. But with farmers, like your usual farmer looks like this, maybe even older. Like they're super conservative in terms of technology. they have their networks from which they actually take all the stuff. Like even innovating in terms of herbicides themselves, they are not really supporting it. So unless the person who sells them the herbicides tells them it is good, they're not going to accept that. So the users are going to be actually the biggest issue for you to implement something like this, because creating something so user-friendly that those people will be using it, well, we haven't actually found a solution for that, so that's something for you. And then there's regulators, but that's something that you probably all have your experience with, because the regulatory bodies are focusing on multiple aspects of technology, and the agriculture ones are not different from the technical ones. Yeah, so let us close with the early adoptions. That's actually what you can be part of, what I would suspect you would be more interested in. That's actually where you can grow and where you can implement this knowledge. That being that there's a certain domination of service-based approaches, basically the 2 or 3 startups I was describing before, where they fly drones, create application maps for farmers, and that's all their business model is. So therefore, outpacing them in the data analysis or creating something that's actually real-time would definitely be something that the market is waiting for. Then there is also the lack of integration. Like majority of those applications are targeted at just one thing, that being, yeah, I detect wheat. Yeah, I show you where there's not enough of a fertilizer. Yeah, I show where there's some sort of bug eating your crop. But integrating it all, because agriculture with the open system dynamics it has so much data, but no one's integrating it. I know it's huge amounts of data. You need, once again, people who understand it. But that's actually one of the biggest potential things for you to actually go into, like integrating all this data and giving something which would actually inform the farmers in a simple, user-friendly way. Now, let me close up with the alternatives, because that's actually the funniest part for me, that there's a research team which gave up on annotating the data. So they basically just used Stable Diffusion to create their own data on basis of like, I think it was 56 species with 20 pictures per each species, and they were able to create a data set which was in thousands. So if you don't like annotations and want just like one person to annotate for you, this is the way. Make your own data. It's not perfect, but it actually works. Then there's also the free satellite data. In all honesty, there's so much data for agriculture available, but no one actually looking into that. So if you would be interested in some difference in something like differentiating your potential company or your potential focus of your company, look at this data. It's free, actually. The Copernicus data, it's freely available for every citizen, and no one's using it. So think of all the endless possibilities for you to actually use this data and create something of a value from that. And then one thing I'm actually working on right now is large language models for farmers. Like, it's super experimental, and the farmers were looking at me with question marks at their faces, because it was like, yeah, I created this for you, try it. And this person was looking at me like that, like. So yeah, that's also something you can try. Now, let me conclude that there's support of economy and there's support of social pressure. So there's a lot of potential for you to actually try to make something of that, because the farmers not only want it, but they actually are forced to do it. Then there's a lot of potential for improvement of the stuff we actually have at the moment. So therefore, don't be afraid of sipping into this data and trying something new, not going just with the normal industry standards, but having some ideas, some innovative approaches. And then there's also the varying levels of competition, like the absent competition being in the 2 or 3 for startups for all of Europe. So don't be afraid. There's not too much competition. It's just about walking outside of your zone of confidence? Comfort, yeah, of your comfort zone. I'm sorry, it's too late. So yeah, think of that. There's a lot of potential. It's just up to you to walk there and take it. Yeah, and the sky is the limit, so go for it. Thank you for your attention.
Thank you, Adam, for a great talk. We have a lot of questions. Sorry, we won't have time for all of them, so I will try to pick some of them, and then feel free to reach to Adam during the refreshments break or after the talks. So, is it possible to make use of data or models from other projects like PlantNet?
Well, the issue with PlantNet is that that was actually the only project that made its data available. But like I was describing before, the data diverges a lot between regions. So even plants which are growing in Moravia can be so different that using them here wouldn't actually yield the results you would be looking for. So compare this to having data. I think WheatNet actually has data from the US, if I'm correct. So therefore, this data might bring some use, but integrating it with local data can actually corrupt your data set. So I wouldn't recommend focusing just on that, but you can definitely try.
Thank you. Another question is about the time. Wouldn't location data and or following the growth of the main plant make the detection more precise? E.g., if main one is tall and all small ones are weeds. Maybe the time, if you would observe the weeds growing.
Well, the issue is that there's like a small amount of time between the crop and the wheat having no competition between each other and having the competitive approach to all the nutrients available. So therefore, yes, you can wait for the crop to outgrow the weeds. But for example, in case of sugar beet, the weeds actually grow usually faster than the crop itself. So therefore, this wouldn't work there. And also, if you would just wait for it to grow faster, then it would decrease the yields based on the competition that would take place in the field. And therefore, the crop itself wouldn't be so big, and you would waste money by just waiting, because the larger the weed gets, it's more resilient to the herbicide. So therefore, you would need to use more of it, or wouldn't be actually able to manage it at all.
Thank you. Another question is about augmentation. What do you think about advanced augmentation techniques like synthetic data generation, different crops, weeds, environment conditions? So if it could help.
Well, having more diverse data would definitely help. Like I was saying at the end, you can actually create your own data with the generative models. So that's something that definitely has its potential. But the thing is that the diversity you are able to simulate with these approaches isn't all that similar to the one that the fields are creating. So therefore, it's something that has potential for use, but it's not going to be so much better than having the real data from the real world. Like if I would put it simply, if you would have just the data from Czechia and would try to emulate the data from other locations, it wouldn't actually be as diverse as the data you would be able to collect from other locations. Like there's a lot of diversity happening because of the different environmental elements which you cannot actually fully simulate.
Thank you. And the last one, could you crowdsource the source data, e.g. farmers taking and annotating wheat and crop pictures via a mobile application?
That's an interesting idea. I mean, I like it. Usually, we haven't tried this because let's just say that one of the issues is that for the herbicide to actually do its thing, you need to enact it on the field quite soon. So therefore, when the weeds are super small, and I remember this one thing from one exam I was talking, where basically we had a bunch of species of weeds, and we were tasked to differentiating between them. And there was this one small plant, and I wasn't able to tell what species is that. So I asked the examiner, and I was like, yeah, I don't know either. So usually need people who are like super into the thing and who can actually differentiate between the small weeds. Therefore, having the farmers is an interesting idea, but usually they can differentiate between the weeds when they are in their adult stage, and that's a bit too late for you to actually effectively manage the plant.
Okay, thank you for answering all the questions. We have 11 more, but sorry, we don't have that much time. So thank you once again. One more applause, please.